including the Natural Sciences and Engineering Research Council of Canada and the government-funded Quantum Major Innovations Fund project. I thank Catherine Reeder for her help along the way as I prepared for the talk. So none of this work would have been done without the outstanding graduate students, postdocs, and collaborators that I have had the great privilege of mentoring and working with over the years. They're spread all across the globe as shown here, with half a dozen of my former students and postdocs and faculty members in various institutions worldwide. I like telling the story that my long-term collaborator, Professor Haduri of McMaster, who sadly passed away recently, after half a century of distinguished research, was mentored by none other than Rudolf Pires in Manchester, was the first to estimate the critical mass of the atomic bomb during the war. I'm a member of these international research groups and consortiums. The pictures in this talk are either drawn by me, or in one instance, a picture of a cat drawn by my daughter, and the rest have all Creative Commons licenses. So this is a rough plan of my talk. Just as the pale blue dot is all we have, the universe is also all that we have. And therefore, it is natural that we would like to know what it is made up of and what are its working laws. In other words, its ingredients and recipe of the cosmos. It is basically this curiosity which drives us. In this talk, I will talk about what we do know, what we do not know, a few new ideas, and then summarize in the end. And I'll be happy to try to answer any questions as best as I can. Now, the way it normally works in physics and in many other disciplines is that one makes experiments and observations based on which one proposes theories or models, as you can see to the right, that circle, which one then uses to predict further observations which gives even a better theory, and the cycle goes on. In the process, our understanding of the universe gets better and better. An excellent example is the theory of gravitation, which was first proposed by Newton, as we know, and then it made predictions. Then most of the predictions worked. Some didn't work. And the ones that didn't work made Einstein propose a modified or a better theory, which subsumes Newton's theory, but even better. And then we are waiting for the next round, next iteration of relativity. So that's the way it seems to work. But first we ask the question, we have this huge universe, how can we scan its immensity, whose visible part is about 14 billion light years wide? How can we scan it without missing anything? Now, one way to do it is we can start from the middle, which is about a meter. It's let's say about a human dimension, and we can either look down or go up. In that way, we can kind of cover everything that's in the physical universe, of course. So if we go down at about 10 power minus 10 meters, the fundamental building blocks become atoms, so electrons, protons, neutrons. And then if you go to, again, another billionth, then the electrons, protons, neutrons, they give way to quarks. So quarks are the fundamental building blocks of matter. And then if you go even further, at about, which we call the Planck scale, which is a decimal point followed by 34 zeros and a 1, if you can imagine that. So that's supposed to be the very basic, very fundamental, nothing beyond that. And at that level, space and time is supposed to be just like foams in an ocean, which we call vacuum. So we do know that the fundamental constituents at the microscopic level, the very basic building blocks of matter out of which pretty much everything is built. It's quarks, it's leptons, it's photons, it's gluons, and the Higgs boson, also known as the God particle. They make up everything around us, including this podium, the cells in my body, and the stars in the heavens. What we don't know, however, so there's an awful lot we do know. So everything that we see is made up of this 18 or whatever number of fundamental entities. That's it. What we don't know, however, is that why we have 6 quarks, why not 8? Why we have 6 leptons, 12 force-carrying gauge bosons and 1 God particle, the Higgs boson. Why we have 3 space and 1 time dimensions? So we can go this way, that way, that way. So 3, and we can go forward in time, not backwards. But in any case, so there's 3 plus 1. Why do we have not more, like 4, 5, 6, 7 dimensions? And we have 4 fundamental forces in nature, and that's also something which we don't really understand why it's 4 and no more. So next we switch gears maybe and look up, like from 1 meter again, and now we look up the sky. So we go to bigger and bigger length scales, bigger and larger distances as we move right of the picture. So in this picture, if you start from the middle, if you go towards the left, we are using bigger and bigger microscopes. If you are going right, we are using bigger and bigger telescopes. So for example, if we start moving towards the right, at 1 trillion meters, we have the solar system. Then at 1 billion trillion, the galaxies. And then at more than 1 trillion meters, the vast expanse of the outer space in the universe. At such cosmological scales, which is, as I mentioned, trillion, the main constituents are quite different, being mainly dark matter and dark energy. And I'll say more about it in due course. We'll talk more about this later, but suffice it to say that this way of looking at the universe also brings into light what are the forces which act at different distances. For example, of the 4 forces in nature, there are only 4, no more, no less. So everything that you see around can be attributed to one of the 4 forces. The nuclear forces act at atomic and shorter distances, the electromagnetic forces as intermediate distances, and gravitational force or gravity at large distances from the planetary to the galactic to the cosmological. The pictures and the dates shown below are the approximate times when major discoveries were made in the above areas, and or a Nobel Prize or 2 or 3 were awarded around that time. So, for example, if you go even like, if you look at the discoveries that are made, you have to go left and right, and the timeline kind of increases that way, right? Because in one side, there was more and more fundamental discoveries being made at the microscopic, and on the other side, there was more and more fundamental discoveries made at the macroscopics. And two of the best examples are quantum mechanics, and you can see the date line, right, around 1925, 27, and also relativity, which is Einstein, 1906, 27, 30. So they were kind of going in parallel. Some of the dates, it's just a handful of the characters here. But for example, on the left, if you see quarks, the discovery of quarks, the Nobel Prize went to Glashow, Salam, and Weinberg. Before that, quantum electrodynamics, where the first quantum theory of first consistent quantum theory of light, of photons, was made. Then that went to Feynman, Schwinger, and Tomonaga. And quantum mechanics, of course, was an enterprise made by the efforts of 20 or 30 years by very bright minds. And that picture, it's pretty small, but that's one of the Solvay conferences picture. It has like, if you look at it closely, it has about 40 people, out of which there are 20 Nobel laureates, some such thing. Anyway, so it's too many to name. and on the right as well, it's of course gravitation, or the whole of physics, and for that matter calculus. Much of it was made by Newton. And then the first major modification of Newton's theory, and very interestingly, was made by Einstein around 1915, and then its development around 20s about cosmology. The interesting thing was that Newton's law, the way Newton put it, it had to be wrong. It had to be wrong because it's incompatible with the propagation of light. So if you want light at, properly, kind of in a proper theoretical framework, then Newton's theory has to be wrong. And then, of course, there were experiments which showed, for example, Newton's theory, if you combine with light, it predicts that there must be ether. Ether is some reference frame in the universe which is special. But the whole point is there's nothing special in the universe, okay? So therefore, it had to be wrong, and it was proven to be wrong, that there was no ether, and that's known as the Michelson-Morley's experiment. But interestingly, Einstein discovered it seemingly without actually knowing that experiment. So I'm trying to say is like, he kind of, just from the point of view of logical, that it must be changed, and that's pretty much how he got his theory. It's an exception though, because as I tried to show in the circle previously, mostly it's experiment and theory, it goes on. But Einstein was Einstein, right? So he, yeah, example not to be followed, absolutely not. His best discoveries was made when he was a Swiss patent clerk, right? But the fact of the matter, so there are these exceptions where Dirac being another, and I'm saying something which Dirac said, and I think is extreme, but I'm saying, so Dirac, Paul Dirac, he's called the theorist of theorists. It's an English guy. And he said, like, if I'm ever confronted with experiment or a nice theory, at the drop of a hat, I'll take the theory and not the experiment. I don't think that's right, because, but he was that extreme, right? He was an extreme theoretician. But in any case, so so that's how it kind of spanned out. Now there's another interesting feature which nature has, and we don't know why she does, but she does, which is around the length scales that we kind of perceive with our simple measuring tools and around us, that is around the middle region of this picture, top middle, so 10 meters to go a little bit. It's a logarithmic scale, but go a little bit here and there. So around that region, so with the eye or simple instruments, nature seems to be classical, governed by Newton's laws and Maxwell's equation, whereas if one wanders too much in either side, it seems to become quantum. So what is the difference between classical and quantum? Well, classically, everything is predictable. For example, the path of a tennis ball, or the trajectory of a city bus, or tides in an ocean, or a path of comets. Everything is predictable, everything is measurable. Whereas when it comes to quantum, the predictability goes away, and we are left with a probabilistic world run by some kind of cosmic dice, where spooky forces emerge, electrons appear magically, where classically they have no business being there, and a cat can be both alive and dead at the same time. Please remember this spooky forces part, because we will argue later that this may actually solve one of the mysteries of the universe. Note that these very counterintuitive things, for example, it's a small diagram, I try to fit things in, but if you see the quantum part on the right, the first picture is that of two dice. The second is a box with both two cats, one is dead and one is alive, because quantum mechanically that can happen. The third picture, if you see on the right, it's an electron, it's from the left, and then there's a big wall, so the electron can't really go there, but it does go there. It just appears there because of the spooky forces of nature. And it is this counterintuitive forces in quantum mechanics that's responsible for example, the transistor, the computer, medical imaging, all kinds of imaging devices, and the computer and the internet. So the rest is history. So note that all these effects are real as we see things around. And in fact, if there was a cat of atomic dimensions, then it would be dead and alive at the same time. And it is quantum mechanics which is responsible for all this. So much of this physics devices developments were done by theoretical physicists, and we can now say safely that basically no quantum mechanics, no progress. So next, right. So one quick thing I want to say, which is, if you look at the arrow in the bottom, right? So on the left you have classical, where everything is predictable and big and everything. On the right hand side you have quantum, which is small, but it's difficult, it's not very clear how to arrive at this deterministic or apparently deterministic universe that we see around us. It must be, well, approximate, almost an illusion, right? Because fundamentally the universe is quantum, there's no doubt about it. Fundamentally, the universe is probabilistic, not deterministic, yet we seem to see a world around us which is deterministic. So there must be a very precise mechanism, a precise prescription by which the probabilistic theory becomes a deterministic one. And that's what we don't know exactly how that happens, but we don't really care. We don't care because the two theories work very well in their own domains. And that's all that we really care. Now, as we argued that simplicity, as we go down and smaller and smaller, right? the universe or the world seems to become simpler because, of course, the theories of quarks and leptons, I mean, there are 6 quarks or something, right? It's not super simple, but it's simpler than having, a big thing like a galaxy or Earth or, like a volcano erupting, for example. They're much more difficult things to model and work with, right? So simplicity. But it can also be argued that, I would argue, that if you look upwards too, the simplicity appears even at larger scales. For example, if we go progressively higher, say from the terrestrial to the planetary, for which Kepler's laws are simpler, much simpler than the planetary laws, then when we go to galactic and finally at about 10 billion kilometers, or equivalently about 1,000 million light years, which we call the cosmological or the Hubble length, the universe looks, as if you can see the picture. So first we start with the terrestrial thing, then we go to galactic. Even the pictures look kind of simpler. Even the fundamental laws are simpler. And when we go to the cosmological scale, what happens is the universe looks like a very smooth fluid, almost like water. And with each particle in the fluid, so each particle, and I believe that's a real picture, right? So the last one, like a telescope picture. So each point in that picture, it represents a galaxy. So at that scale, the universe is really smooth. It's really smooth like a fluid, and it's really simple. So our pale blue dot is orbiting 1 in 100 billion dots in a galaxy, which is 1 of 200 billion dots in the observable universe. So it does make one feel small. But on the other hand, these observations in a way are a continuation of the realization over the ages that we are not special and we are not the center of things. We are not the center of anything. We are just one of many, many, many. Which astronomers and philosophers such as Copernicus, Bruno, and Galileo, shown there, had asserted. And far away from the left hand, the Ptolemaic universe where Earth was the center of things, which is wrong. While this seems like a pretty simple and even a refreshing statement that we are not special, it's kind of liberating in a way, and reflects humility, keep in mind that one of them lost his life and the other liberty for saying just that. And yet it moves, Galileo had declared, to the Inquisition in defiance, and move it does. So the instruments used to observe the physics at large distances are, of course, telescopes. Here we have a snapshot of the earliest telescopes, for example, that made by Galileo or Newton, to the Planck satellite, to the Hubble Space Telescope, and its successor, the James Webb Space Telescope. So these are all telescopes. Now there are a few points to make here. One, the resolution of the telescope has increased like 1,000-fold. So we have come a long way from when Mars appeared as a kind of a dim red spot in the eyepiece to getting a clear picture of a soccer ball at 500 kilometers, and that is the current resolution. It's amazing. The second point is visible light is not the only messenger of information. In fact, many of the mysteries of the universe, including black holes and unseen star clusters, are revealed not through visible light, but through electromagnetic radiation in the infrared, ultraviolet, and X-ray range of the electromagnetic spectrum. In fact, my departmental astronomy colleagues make some very fine instruments which go up into space and make measurements in the infrared region. If anyone's interested, you're welcome to get in touch with them or with the department. The next point is that gravity wave detectors are like the new kids in the block. So they're all telescopes, and they all measure light, if I can say infrared as light as well. I mean light in a kind of broad way. But recently, last 10 years or about that, there's a new way of measuring things in the cosmos have come about, which are gravity wave detectors. So what happens is something like this. So gravitation, Einstein showed, is nothing but a space-time artifact, meaning that if you have a large, very massive object, like a black hole, talk about black holes a little bit, then the space-time around it is curved, it's warped, it's like a well. So anything around it kind of moves around, right? So it's the mechanism of gravity is not because something is pulling that object, but this object is making a dip in the ocean of space, and then that object falls in that dip. So that's the picture. And if that's the picture, then for example, if two black holes merge, it's a very violent event. And due to that event, the space-time itself around it gets distorted. And then the ripples of space-time also travel at almost about the speed of light. The ripples of space-time come and hit anything that's here, right? But the ripples are very small. So you need, I forget the exact numbers, but you need like big bars, like big metallic detectors, which are like hundreds of tons or something like that, and hung by very thin wires. And when this space-time ripple comes and hits those bars, they move a little bit. And that little bit movement is detectable by laser. So that's how it works. And the amount of movement of these bars can be as little as 1/200 times the size of a proton. It's crazy, right? I mean, it's like, and that's in fact one, like, maybe a digression, but at 100, or rather 1/200, the size of a proton, the world is quantum, whether you like it or not, right? So even though gravitational waves are classical things, like predictable and everything, to make that measurements at that scale, you have to bring in quantum mechanics, like there's no other go, right? So that's just a comment. But with all the above instruments, and then there's another third channel of measurement with neutrinos I wouldn't be talking much about in this talk. One observes the cosmos, and observe they did. Incidentally, none of these pictures that you see here are in the visible spectrum. In fact, the first picture in the bottom on the left is in the infrared. The middle picture is in X-ray. So it's X-ray, but you know, it's false color, right? I mean, you can't see an X-ray, but I made some color code. And the last one is gravitational wave. So the wiggle that you see, like it's a sine wave or something like that, it's actually a gravitational wave hitting, and the gravitational wave was created when two black holes merge or two neutron stars merge. So it's amazing we can actually see it right from here. So if you, so and what did they observe with all these instruments? Well, the first thing that they observe is an extreme uniformity wherever you go. So let me try to explain. If you take a look at this picture of the cosmic microwave background radiation, or CMBR as it is called, this is like an infrared thermometer picture stuck in the sky. And this picture, firstly, it's a picture of the whole sky, right? So it's a certain projection. It's also done, for example, if you look at the map of the Earth, it's written in that way so that it's projected in that way so that you can see the whole Earth, right, on a flat surface. So it's that. So what's described here, this whole thing, it covers the whole, like, not like northern hemisphere, southern hemisphere, everything. And so showing a temperature, and this shows a temperature of about 3.7 degrees Kelvin, which is, if you like, the temperature of the universe right now, okay? Created from the heat from when the universe was much smaller and hotter. So this is the heat from smaller and hotter. It cooled down, and it's cooling down continuously. Right now, it's 3.7. Tomorrow, it'll be 3.1. By tomorrow, I mean like 1.5 billion years, something like that. Well, everybody has their own scales, right? Geologists have million years as their time scale. We have 1 billion. So nothing less than 1 billion. I mean, we're not worried. Anyway, so first, so that was that. Second, this may not look very uniform, but the different colors depict different temperatures, okay? So yellow is hotter than the blue, or so some color code. However, the difference between the, or did I say it wrong? I think blue is hotter than the yellow. But anyway, the difference between the hottest and coolest spots in this map is only about 100th of a thousand of a Kelvin, hundredths of a thousand of a degree, right? Therefore, in effect, this is actually quite uniform. So the only discrepancies that you see is 1 part in 100,000. So it's pretty uniform. And this incredible uniformity is a manifestation of the uniformity of the underlying space-time structure of the cosmos. So what did they see? What did they observe? The first thing that they observed with these telescopes is that the universe is the same everywhere. It is homogeneous. Whether you're here at point A or point B or point C, you'll see exactly the same, okay? Second observation, the universe is the same in all directions. It is isotropic. So whether we look in that direction or in that direction or in that direction in the sky, it will look exactly the same on the average. Well, if you ask, well, it doesn't look the same, well, that's because we are looking at shorter distances. Again, just like we talk about billion years, for us, like, a decent length scale is about 1 billion light years or something like that. And if you go to that length scale, it does look like this perfect fluid, It does look like just pure water. Okay, so and third point is that Euclidean geometry or Euclid's postulates, the Pythagoras theorem, everything holds good even as the cosmic or the cosmological scale. It didn't have to. So if you did make a triangle joining points A, B, and C, which are 3 galaxies far apart, again, 1 billion light years or something like that, the 3 angles would indeed add up to 180 degrees. And, I as a parent can say that, like whatever, my daughter, whatever you learned in class in geometry, it's all correct. I mean, it's not wrong, right? So Pythagoras was right. And Pythagoras was right not only at the small length scales, but Pythagoras was right at the cosmic length scale, which there's no reason for it to be that way. And interestingly, these 3 observations, that it's homogeneous, that it's the same everywhere, so we are not special, is the same in all directions, we are not special. And the fact that Pythagoras theorem hold, that's why I kind of try to emphasize is that Euclid's axioms are valid, that 2 straight lines, like parallel lines, don't meet and that kind of thing. These 3 immediately, actually, mathematically you can prove, and mathematically you can show that the only consistent universe which can have these features, these 3 features, is an infinite universe. Okay, so the universe is indeed infinite. There's no other go. Okay, if it's a finite universe, then Pythagoras theorem will not hold good. Just as if you have a sheet of paper, of course Pythagoras holds good. But if you had a sphere or a saddle, Pythagoras wouldn't hold, and the sum of the angles of a triangle will either be big for a sphere, greater than 180 degrees, or pi radians, or if it's a saddle, then less than that. So Pythagoras theorem and Euclidean geometry will not hold, but it does even at these scales. So it means it's infinite in extent. So when I mention the size of the universe, if it's infinite, what do I mean by size, right? I mean one of the 2 following things. Either the relative distance between galaxies, which makes sense even if you have an infinite universe, because that can increase or decrease, or the Hubble radius, or the cosmological horizon, which is the farthest we can see at present. So even if you had the most powerful, like made with like infinite dollars or whatever, telescope, the farthest you can see right now would be 14 billion light years away. It's just that we don't see beyond that. That's our horizon. So the universe is beyond that. It's infinite, but it's like a sphere. And it's not your sphere or my sphere. Whoever is in the universe, you draw a sphere, 14 billion light years of radius, that person will see up to that. So it's like a universal horizon of the universe, if you like. So in this impression, each dot represents a galaxy, and their utter randomness, as you can see, and ubiquitousness show beyond doubt that every point is the same and every direction is the same. So you can get a feel that, like, it's all random, right? It's all random, it's very dense, and it's everywhere. Therefore, how would you choose a direction? And it's basically as simple as that, okay? So the universe does appear to be uniform, homogeneous and isotropic. And as I said, any inhomogeneity or anisotropy is kind of a short distance effect. Note that, as I said again, that there could have been an infinite number of other possibilities, and it needn't have been this way. So our universe is indeed a very symmetric thing. Before we get back to the evolution of the universe and what happens to it, let us get something out of our way. In particular, at galactic scales, okay, we have something which is intriguing and fascinating in equal measure. And in fact, it may hold a key to the ultimate fate of the universe. That's why I thought I'll take a little 2-slide digression, and I'll come back to cosmology. These are black holes. Black holes are objects predicted by Einstein's theory. Einstein's theory is correct, so black holes must be correct. And black holes have been seen. In fact, black holes which are supposed to absorb everything, including light, everything, nothing comes out classically. They appear, or they exist at the center of every galaxy. In the picture there, the left-hand side is, of course, the artist's impression, and the right-hand side is actual extra picture of a black hole with the dark center being that black hole. And as I said, they exist at the center of every galaxy. The one at the center of our own Milky Way weighs about 1 million solar masses, and it's called Sagittarius A star. Due to uncertainty in quantum mechanics, so if there is quantum mechanics in one line would be, you could either say that, as I said, like, things would be there where they were not supposed to be, right? It's probabilistic. Or, whatever you think is going to happen definitely is not going to happen. So quantum mechanics is like that. But
So classically, Einstein's theory says that nothing can come out of a black hole, but of course he must be wrong, because he didn't take quantum mechanics into account. When you take quantum mechanics into account, a little bit of thing comes out, okay? Just as the electron can be on the other side of the wall, just a little bit, maybe of 1 million electrons do get on the other side of the wall, but that too are responsible for transistors and computers and everything, right? So here too, a little bit of radiation comes out of the black hole, but it contains very little information, which means as the black hole gives out a little bit of radiation, but eventually it's going to evaporate, a lot of the information that went into a black hole, and a black hole absorbs a lot of information because it's heavy, everything goes in, nothing comes out. So all that information is irretrievably lost. Now, and that's a bad thing. It's not a good thing. Why is that? It's shown pictorially here, the situation, where a laptop, let's say, or a painting containing lots of information, terabytes and terabytes of information, falls down a black hole. Well, I sometimes wish that my laptop does fall down a black hole, but that apart, what comes out in the end is just hot thermal radiation with the black hole evaporating away. And why is that not such a good thing? Because technical details notwithstanding, the quantum mechanics that we know says that it is impossible to destroy information. Believe it or not, it's impossible to destroy information. You think that information is destroyed, but it's still hidden somewhere, and you can always kind of recover it. Maybe not. Maybe it's a technical issue beyond the point. I mean, if I take a hard disk and kind of smash it with a hammer like for 3 hours or something, maybe it's irretrievably lost, but that's more of a technical issue, okay? So, so even, let's say, if you burn, let's say, a secret letter in a fireplace, as shown there, a sufficiently smart detective with the right instruments, maybe with some thinking, and also maybe with the help of a little bit of a cigar and some whiskey maybe, should be able to completely decipher what was written in the letter, in principle. So, and that is quantum mechanics, which, if you, as we remember, is a correct theory. So if we accept quantum mechanics, we accept this. But Einstein's theory says, no, information is lost. Therefore, long story short, either quantum mechanics is incomplete, or Einstein's gravity is incomplete, or both are incomplete, right? And thank God, we have work to do. So it's a logical conclusion, right? The two theories are incompatible. You cannot make them compatible with each other. So at least one of them must be wrong. And it's quite possible that they're both kind of have to be changed. Now, let's come back to cosmology. Let's spend a couple of minutes on what the telescopes actually measure and what they tell us. Imagine for a moment that you live near a train station. So a locomotive comes from the right, quite a distance away, and approaches you at a certain speed, okay? The whistle is heard as a low volume, high-pitched whistle. Low volume because it's far, as you can see there on the left, and high-pitched because it is approaching you, and Doppler effect, that's what it does to whistles. Next, consider a second train from the right, which is bigger because it's much closer, but receding from you. Its whistle would have a higher volume and a lower pitch. Higher volume because it is near, and lower pitch because that's what Doppler effect does to a receding source of sound. So by listening carefully to the whistle of a familiar locomotive, if you listen carefully, one should in principle be able to determine the distance and speed and even the acceleration, if any, of the locomotive, in principle. Next, if let's say there's a tree, as we see on the left, or a house on the right, intervening between the sound and the observer, or the listener, okay, that would affect the sound as well. So again, a careful listener with accurate measuring apparatus may even be able to tell more or less if there's something in between, and if that something was a tree or a house, or something like that. So a lot of information can be obtained. Now imagine we translate this to light. Okay, so imagine there's a 100-watt light bulb. We know how bright it intrinsically is, right, the light bulb. Next, if we move the light bulb, say far, its observed brightness falls, of course, right? And in fact, there's a precise relation, like if you move the light bulb by 1 meter or 10 meters, there's a precise relation of how much the luminosity that you see, the brightness that you see would decrease. So you can turn the argument other way around and say by observing how much brightness we see and knowing that it's a 100-watt light bulb, we can estimate the distance It is away, right? Furthermore, now if the light bulb is speeding away, as you can see in the second picture, it's kind of moving towards the right. In that case, Doppler shift will affect the light bulb as well. So the light bulb will become redder. And then by measuring the color of the light bulb, we can determine the speed of the light bulb. So if you measure the intensity or the brightness of the light and the color of the light, you have full information of how far it is and how fast it is going. In fact, now if it starts to accelerate, it becomes even redder, maybe crimson. And again, from the color and how fast the color is changing, you can determine everything related to the speed and acceleration of the light bulb. Even more, if there's a different kinds of matter given by those, like, or shown by those boxes, green and yellow, intervening various forms of matter and energy, like dark matter, dark energy, whatever, if it's there, that will change the quality of the observation. And therefore, by observing that, one can also determine not just the motion of the light bulb, but also one can infer about the acceleration and what's intervening between the light bulb and the observer. So the reason why it's important is that when one observes the cosmos, that's pretty much one can do, right? One can observe the intensity of the light, right? How bright the light is, right? One can observe how red or blue the light is, and one can observe how fast the color is changing or how different the color is than if there's nothing in between, from which one can say what the acceleration of that object is and also what's between, what's the matter that's intervening. In the cosmos, we don't have 100-watt light bulbs, but we have something better. We have cosmic light bulbs known as standard candles whose total light output is known. So these are like known 100-watt kind of things in the universe. For example, the Cepheid variable stars on the left, supernovae in the middle, and supernovae are exploding stars. So they run out of fuel, but gravity is kind of trying to contract it, right? Trying to bring it closer, and there's no nuclear fuel to kind of contract it. So at some point it can't deal with it and it just explodes with a lot of energy. So they're exploding stars at the end of their life, accompanied by a huge and, more importantly, a predictable light burst. For example, a supernova seen from Earth in AD 1054 was recorded in many ancient texts, including one in Chinese here. Yeah, a friend of mine who was Mandarin literate once told me that he could almost read supernova written there, but he made a lot of other claims as well. So I'm not sure of that. But the fact remains that the total power output of a trillion watt of the supernovae makes supernovae a very good tool for the astronomer. Okay, so and also they abound in the universe. And if you point your telescope to any random small patch in the sky, and these numbers have been seen and calculated, it is very likely that you will see a supernova at work within a week or so, about a week. So in other words, wait for the supernova to shine and observe them with your best telescopes. And of course, it's easier said than done, but that's essentially the idea. So what did they see? So first, let's notice the similarity between the two diagrams, okay, on the left and the right. They basically plot the velocities of objects versus their distances, be it stars on the left or supernovae on the right. The one on the left, taken from Edwin Hubble's 1929 paper, and using stars, while one on the right is of 1998, done with supernovae. So in either case, if you look at the graph, so along the x-axis is distance and the velocity, and as the stars are further and further away, the speeds are higher and higher, as you can see with those 3 stars kind of cartoons on the right-hand corner. The only inference that you can draw from here is that, the only conclusion is that our universe is expanding. The rate of expansion is known as the Hubble parameter, rightly named after Edwin Hubble, which is about 70 kilometers per second per megaparsec, meaning that every megaparsec, and a parsec is 3.3 light years, so mega is a million of that. So every megaparsec you go further, the speeds increase by about 70 kilometers a second. Before proceeding further, we note that theoreticians, again, such as the Russian astrophysicist Alexander Friedmann, who you see there, and the Belgian priest, Monsignor Georges Lemaitre, predicted such an expansion as a distinct possibility just with using pen and paper. That is, the power of theoretical research. So they predicted that, in fact, a few years before Hubble, that this is quite likely the possibility. Very few people believed them, but then, Hubble found it. There you go. Now notice the difference between the two pictures. Can you see the difference? So look at the picture on the left and the picture on the right. So they're both velocity versus distance pictures. If you look at the difference, while the first covers distances on the left of about 100,000 light years, the second covers larger left shapes and up to about 1 billion light years for supernovae, right? So the second obviously carries more information, although of course it took 70 years to reach this stage. So I go to the next slide where I show it again, and I don't know if you can see it or not, but as we go towards the right, if you notice carefully that the picture, the supernova picture, if you go towards the right, the best fit curve of the observations deviates from a straight line. You can see that a straight line doesn't, the points are the observations, like light observation, the supernova. So each circle or a point on that picture is one supernova, right? And the more right you go, the further is that supernova, again a few billion light years away. And the intuition or the expectation was that they will all fall on a nice little, nice straight line. Well, it does to a certain extent till half of the diagram, but then it starts deviating, like wandering from the straight line. What does it mean? Well, it means a lot. It means any deviation from the straight line means that the universe is now accelerating. Well, accelerating or decelerating, but the fact that it curves upwards, not downwards, when it's accelerating, meaning that it means it's expanding faster and faster every second, and there must be some element of anti-gravity out there to make it happen, because gravity cannot make things speed up. Imagine a device which, for whatever reason, it explodes, and the shrapnels fly away, but they slow down, right? They fly away, but they slow down. They don't spontaneously start, in a runaway mode kind of thing, right? So gravity can't make things accelerate, and the fact that we see the universe accelerate, that's irrefutable, because that's seen with the telescope. What can we do about it? And since it's seen by a telescope that the universe is accelerating, it means that there must be a huge element out there which overwhelms gravity, and which we can call anti-gravity, and later we'll call dark matter. So remember that observing the colors of light gives information about the matter content. It's exactly that. And looking at this curve very carefully, one has concluded that the universe consists of 5%, only 5% of ordinary matter. Okay, ordinary matter is this kind of matter. Okay, everything that you see basically, okay, which we see around us. 25% of dark matter, which is not visible, but we know it's there due to its gravitational force, and about 70% of dark energy or cosmological constant, which has a negative pressure and serves as a source of anti-gravity. So that circle sort of, that pie diagram sort of shows it. So the yellow slice, that's all that we see, everything around us, everything in the universe, okay? The blue is dark matter, and it's about 5 times that yellow slice. So the amount of matter we see, the amount of matter we don't see is 5 times that, and that whole red part is anti-gravity, which makes it accelerate. So it's actually, so as you can see, 95% of the universe is really unknown. We know it's dark matter and dark energy, but we don't know what exactly they are, right? The results were so surprising, but so correct, that the Nobel Prize in Physics was awarded in 2011 for this discovery to these 3 amazing astronomers, and you can see them quite happy there, and rightly so. They just found out what the universe is made up of, and that it's accelerating. I mean, they should be happy. So based on these observations, in this slide, we show how the size of the visible universe, again, the vertical line is the size, and if you ask, it's infinite, so what do you mean by the size? So that size could be the distance between 2 reference galaxies or 2 very distant objects, right? And on the right, time flows. On the left, there could be a start of the universe or not, but we set at t equals 0, say 14 billion in the past. So right now, we have the cosmic microwave background radiation and the galaxies and stuff, and then we have the future. So this shows how the visible universe changes. Since it has been expanding for a while, it must have been small at some point, right? It's expanding, so it must have been small. Whether or not it was created in a Big Bang moment, but this was it was very small, about 14 billion years ago. That's for sure. Then we had a period, of a few billion years, when quarks, gluons, electrons, and photons were in a hot soup, in a hot plasma, because they're so hot that nothing could form, right? It's so energetic. So it cooled down as the universe expanded when elements and galaxies started forming, and that's how we are. So this is where we are now, and in future, there is a distinct possibility that acceleration will rip the the universe. Trust me, it's Freudian. No, not Freudian. Well, the university represents the universe, and vice versa. So anyway, so coming back, so the universe might get ripped apart as a distinct possibility. Now, telescope observations. Now, so what can we say about the origin of the universe? So here I draw a simplified picture. Okay, so we have a simplified picture of the expansion of the universe. Now, telescope observations give a very solid picture of what the universe was like until it was very small, about 14 billion years ago. Then there was a gray area. It doesn't mean there's something really gray and solid out there. It means there was a region, again, about 14 billion years ago, below which the universe was so hot, so energetic, that our current laws of physics would break down. So you can say nothing about it, right? So therefore, any prediction, for example, that of a creation of the universe in the Big Bang, or anything else, any prediction made at that very, very early era would be at best speculative, okay? That's not a criticism, that's the way science is, right? So any conclusion, but on the right we have like up to that, that kind of, that gray thing, we know very well what happens. Or there's another possibility, or we could have something like this on the right, where right now we are in an expanding phase, which was preceded by a contracting phase. Nothing funny happens when it's small. It's smooth, it's just small. It's not like zero. So there was a contracting phase, then it became very small, then it became an expanding phase. And this is perfectly consistent with the observation. So that's also a distinct possibility. Big Bang is more popular in certain ways, and there's nothing. Even those who say that Big Bang happened would also say that, like we know only up to about t equals minus 14 billion years. So this is also a distinct possibility. And this is completely consistent. And in fact, many cultures across the world have spoken about such an interesting and everlasting or even a cyclic universe. Second, the problem of dark matter, right? The potential existence of cold and hidden matter was speculated earlier, following the observations in the 1930s. So this is dark matter, although the supernovas do give very, very solid evidence for dark matter has been around. So it was first speculated in 1930s by Fritz Zwicky, who was a very interesting Swiss-American character in Caltech, who used to refer to his colleagues as spherical bastards, because according to him, they're bastards whichever way he looked at them. So he was that kind of guy, right? And there are other even less generous jokes attributed to him. But in any case, so he was the first to observe that he concluded there must be something out there. And then there was Vera Rubin, the American astronomer, and one of the first recognized female astronomers whose observations of galaxy rotation curves in the 1960s clearly showed that there was something more out there than what meets the eye, since Rubin's pictures, if you can see, so the graph on the left, that's Vera Rubin's observations, and you can see that Newton's prediction is in the bottom, and the observation which she made is the top, and there's a huge amount of discrepancy. So there's way more rotation than you can see. So there must be something, okay? So the question is, what is this invisible matter, or dark matter? There has been many dark matter candidates and proposals. For example, fuzzy cold dark matter, weakly interacting massive particles, supersymmetric particles, supersymmetric axions, Chaplygin gas, gravitons, gravitinos, neutrons, neutrinos, neutralinos, Q-balls, Higgs, dead black holes. Did I miss any? And what's common between them apart from the fact that they all try to explain dark matter? Anyone? In all this plethora of ideas? Well, the other thing common is that none of them have been detected, okay? Although instruments have been dedicated to find many of them so far. So dark matter remains an unsolved, unchecked in the sense that unverified as to what exactly it is. So the problem is a very, very open problem. one way out of this conundrum is to try to change the theory of gravity itself, right? And get rid of the problem. We don't believe in gravity. No, but there are serious physicists who have been working on this radical idea for a while, but there has been no resolution of that. So in this talk, although it's a possibility, I'll take a more traditional view and confine myself to the overwhelmingly accepted idea, let's say, that dark matter is out there, we just have to find it. The third problem is that of the cosmological constant, in that an unexplained 70% of the total budget of the universe, also known as dark energy. We don't have a clue as to what it exactly is, and when we don't know what something really is, we give it a name. In this case, we call it dark energy. And looks like we know something more. Well, we do, but there's more things we don't know. On the one hand, if there exists a negative pressure, and this is what making the universe accelerate faster and faster. But so on the one hand, it's known that 70% it exerts negative pressure. It's the cause of acceleration, and sometimes it's also called the cosmological constant. But on the other side, and it's usually represented by this big sign lambda, the Greek symbol lambda. But the problem is about the origin of lambda. So the best theoretical predictions and that has been made of this cosmological constant, the best theoretical predictions and the observations, they differ, okay? And by how much do they differ? They differ by something like 1 followed by 100 zeros. So it's like ridiculous, right? So it's not a 1 followed by 100 zeros. That's a discrepancy between the two. Now, cosmology used to be a very challenging observational science, right? Like it's a very difficult science. And things like the Hubble parameter or other observables were often, the error bars were often 50%, 100% because it's so difficult, right? So Hubble parameter would be 70 plus minus 50 or something like that. But the joke is that this kind of discrepancy, 1 followed by 100 zeros, is bad even for cosmologists. So clearly that's not the answer, right? Then why am I saying that? Well, because, and I'm not going to the details right now, but those theoretical calculations are made on very solid ground. So just because it differs by 100 orders of magnitude is not rational enough to just throw it away. In fact, not at all. So there is this discrepancy out there, and we have to somehow deal with it. So that's the problem. Now, it's often said that 2 heads are better than 1, and sometimes 2 problems are better than 1. Let's take stock of what is required of dark matter and dark energy candidates. Well, dark matter must be cold, otherwise we would have felt it. It must be dark, of course, we don't see it. It must be attractive. Cold, dark, attractive sounds like I'm talking about some 1950s Hollywood hero, but that apart, let's also for a moment assume that it is quantum in nature. Let's just assume it's quantum in nature. Also, we know that dark energy must be equally important. In fact, 3 times more important, like 25% versus 70%, so about 3 times. If not more, repulsive, it must be repelling. And let's assume also that it's quantum in nature. Now, remember the spooky quantum forces that we talked about, which are spooky, which are counterintuitive, but which are real. That's, again, what makes computers and transistors and things like that. That seemingly pops out of nowhere. Well, actually, it has quite a few interesting properties, the quantum forces. First, it is approximately equal to the classical force that's kind of in that region. But it's opposite in sign. And so the quantum force that appears in quantum systems, any quantum system, is about equal and opposite to the classical force. And the slight mismatch between the two, it's like plus 5 and minus 4.91 or something like that. That slight mismatch between the two is responsible for all the quantum magic that we see in the universe. Now there exists such a cold, dark quantum state, which is known as a BoseEinstein condensate. So why not assume that dark matter consists of a BoseEinstein condensate, and the quantum force that any quantum device or any quantum system would offer would be the dark energy? Why not postulate that? So let's talk a little bit about Bose-Einstein condensate. This is the Indian physicist Satyan Bose. not the guy who makes Bose speakers. And, and this is the Italian physicist Enrico Fermi. All fundamental particles in the universe are either bosons or fermions, named after them. But when cooled down to very low temperature, like close to absolute zero, like a couple of degrees Kelvin, the fermions are depicted on the right-hand corner with those arrows. The fermions tend not to like each other's company, and they tend to spread out very fast. These fermions are like antisocial, okay? While bosons, at the same low temperature, are very happy to cluster together into what is called a BoseEinstein condensate, or BC, which is nothing but a giant macroscopic quantum state. Okay, so that's a fundamental difference between bosons and fermions. Fermions, you try to like cluster them together, they rebel, and bosons are really happy. But we are also happy, because if lots of bosons cluster together, we have a macroscopic quantum state, which is not easy to muster, right? So assume that dark matter is a giant Bose-Einstein condensate, such that its gravitational attraction is dark matter, and quantum repulsion is dark energy. Now, what about the details, right? Well, precisely to avoid awkward conversations such as this, where one professor shows some math and some apparently important result in the end, at which the second professor asks if it would be a little bit more explicit in the middle step, okay, where it says apparently a miracle happens, and to convince you that I'm not bluffing, that I actually did the calculations, I can show you this, and this, and this, and this, okay, and this, and this. And if anyone's interested in the details, I'll be happy to explain it to them over a beer, or something stronger, or both, taking as long as it takes. But seriously, the pen and paper is pretty much all the instruments that the theorists use, along with the laptop and lots of coffee. But for now, you are welcome to trust my results, peer-reviewed and published, that the upshot is that the numbers work out almost exactly as what is needed. Namely, that the attractive force of dark matter, or a Bose-Einstein condensate, and the quantum repulsive force that the BEC produces are approximately equal. Also, so this BEC, by virtue, but through its mass, can be a viable source of dark matter, while its quantum repulsive force a source of dark energy. The observation that the Bose-Einstein condensate can be a source of dark matter, this had been proposed earlier. But to the best of our knowledge, the fact that one can get sort of 2 for the price of 1, and while the density of the BEC can serve as dark matter with its attractive gravity, while the quantum force as dark energy, we were one of the first to propose that and also work out the detail. More work needs to be done, of course. And why is it almost exactly? Well, because we have made certain simplifying assumptions in our analysis. For example, that the expansion of the universe is not too fast. Now, too fast or not too fast, it depends on more precise definitions, which we have. But if we don't, so for as long as the universe can be considered to be not expanding really, really fast or quick, which we can relax. So, if we relax that, the discrepancy kind of comes down, and we get even better results. Now, one can have the best theory in the world, but nature may not care, right? So data is key to the test of any theory, right? So if it doesn't check out with observations, then too bad. Go back to the drawing board. We did all these, and the graphs show the result of our comparison of our work with the Hubble and Supernova data. So let me explain a little bit. The way this comparison is done, and the data part, how to compare and all, like, I'm still learning. And it's fascinating. It's a very interesting area of research in still. It has to do more with statistics and Bayesian statistics than physics. And one can imagine the observed data are very messy. They have lots of errors. So what one does is something like the following. Using both the available data and the theoretical model at hand, it could be our model, it could be lambda CDM model, it could be some other model, powerful Bayesian statistical methods are used to predict the most likely value of the various parameters and their respective errors. So, for example, if you look on the left, agree it's a bit small, but focus on any of the. So let's look at the middle picture, which has these two arrows. Okay, so on the x-axis is dark, like the proportion of dark matter of the universe. So it's between 0 and 1, right? So 0 being nothing and 1 being something, so everything. That's 100%. And on the y-axis, it's dark energy. And if you see that particular square, the clustering shows that it's like contour plots, right? So where there's lots of cluster, they're the most likely places where these parameters would lie. So the most probable values. And if you go away from it, they become less probable values. And when it becomes white, like the parameters don't lie in that range. So they're very, very unlikely. And if you look at those red arrows where they pretty much point almost exactly at 0.3 and 0.7. Okay, so 25%, 25 plus 5% visible matter, so 30%. So 0.3 and 70% dark energy. So as we can see there, that this shows that not only our model is compatible with observations, but it does fit the data quite well. With the maximum likelihood of dark matter and dark energy being well within observed limits, in fact, centered around their most likely values that was predicted anyway, which is 30%, 0.3 and 0.7. Finally, we come to the fate of our universe. Well, at this rate of an increasingly crazy expansion of the universe, in about 5 or 6 billion years, it will get crazier, and galaxies will race away from each other with no connection between the two. So although their internal integrity maintained by gravity may be maintained for some time, the sky will be dark. It will be real dark, I mean, because the universe will be expanding faster than the speed of light if it goes at the current rate. So all that I'm saying is completely consistent with the current observations. But there could be other things which are consistent well. So no light can travel from one galaxy to another because it's expanding at the speed faster than that of light, right? So galaxies would be like real islands in itself. And when we see up in the sky, we see a lot of stars, a lot of galaxies. Pretty much everything outside the Milky Way will be dark, right? So it will be a very, very dark universe. The good news, well, the sun would likely have exhausted all its fuel by then, and so observers would become scarce as well. Kidding. But there could be some actual good news, which is that the universe could turn around, right? It's also perfectly consistent with observations. So due to new forces, possibly quantum forces, or it could be an everlasting universe, or listen to this, and it's a distinct possibility as well, or we and everything around us could be swallowed by a big black hole. And it's not so bad because we'll be sheltered by its event horizon inside from all kinds of misbehavior outside. Okay, so we would be completely and forever sheltered inside this event horizon, not having to bother of what ever bad is happening outside. Okay, well, I mean, fingers crossed is all I can say. So I end with a quick summary, and to me at least it's quite remarkable that the universe is pretty simple, it's very uniform, it's big, it's expanding, and it's accelerating. And also it's quite remarkable to me that we have a fairly good understanding of what it's made up of and how it works, standing on the shoulders of giants, of course. However, we do not know whether it started at a single point, or whether it is everlasting or cyclic, or whether it will last forever, or end in a so-called big rip. Again, like the way it's accelerating, if nothing happens, then that's a very, very likely scenario. Can we do anything about the big rip? With current technology, maybe not, but who knows? NASA recently showed that it can, in principle, change the trajectory of an asteroid hurtling towards the Earth, so anything is possible. Furthermore, as mentioned, our universe can be cyclic or maybe sucked into a big black hole and thereby protected forever from destruction. I would bet on the cyclic universe just because it seems safer. Black holes are scary. I work on them, and they're scary. Well, time may be short, but time will tell. I thank everyone for your attention, and thank you everyone, and I'll be happy to answer questions as best as I can. Thank you.